Welcome to this class on aspects about product and production, part 3. This is the third part of this sub-module dedicated to product and production aspects within the general module on the technical analysis of a project investment. The outline is showing two main items. So we will deal with two subtopics today. The first one is the study of machinery and equipment. The second one is the plant capacity issues. So just to create some links to the previous classes, we're familiar already with the idea of product, we're familiar with the idea of materials and supplies. Today we will deal with another important component of production process, which is machinery and equipment, as well as we will deal with a crucial decision on plant capacity that we will continue during next class. So let's start with the first element, study of machinery and equipment. Machinery and equipment is related to the selection of machinery and equipment to meet the production requirements is one of the major engineering responsibility. Now, if we are dealing with the so-called turnkey projects, where the company or the project is just buying a solution from a provider, then the technology is chosen by the supplier and the company is just trusting the supplier about the specifications of such solution. It's trusting the supplier about the knowledge which is embedded in the machinery and the equipment that it's buying. Otherwise, if we have an internally designed solution, project designer are the ones selecting machinery and other equipments according to the expected technology they intend to use in the production process, according to the expected standards they are going to embed in the products and in the production process itself. So it's about the choice of machinery and equipment. It's crucial to have in mind the production requirements, and it's a responsibility by the actors guiding this decision within the company and the project. So some guidelines for machinery and equipment selections are required. So the selection is based upon technology, as we were saying, which is embedded in the choice or chosen by the internal designers of the production process itself. The unit's operations for industrial processes is another very important element. So traditionally, the distinction between batch productions and continuous production is very relevant in order to choose among different alternatives of machineries and equipment. Again, the balance of capacity of all stages. This is another important element, and we will momentarily show that the combination of different machineries or the different equipments during different phases of the same production processes, it's very important. So it's the coordination, the integration, the synchronization of such machineries. It's very important for the enhancement of the installed capacity in a feasible terms. Automation appropriate to scale and setting. So basically there is a trade-off between automation and its cost and operation and its cost structure. So we might have some automated activities deployed by robots, for example, And on the other hand, we might have setting issues related to the fact that for each single production or for each single version of the same product, we might require setup times. So, as we've seen already during our past classes on the subject product and production, if we have setup time and setup specific resources, then we have setup costs as well. Suppliers, the choice of machineries and equipment is dependent on suppliers of technology as well. So considering the location where the investment is taking place, considering the area, considering the industry where the company is operating, the role of suppliers is crucial for technology availability and for technology support as well. So when it comes to supplier, it's not just the transaction enabling the project or the company to buy specific technological solutions, it's also about maintenance of the machinery and equipment as well. Performance guarantees. This element is very important since at the beginning of the project or ex ante, it's quite difficult to predict what are the dynamics of aging or obsolescence of the machinery as well. So, in order to buy the best solution, the performance should be predicted and set up and explicited in the deals, which is relating the buyer to the supplier. And then we have the equipment life. Again, it's not just about aging, it's about obsolescence, it's by the company not being able to keep up with the technological development. So if competitors are taking advantage of technological development, our company could suffer from the disposal or the availability of an older technology. So, in order to deal with the so-called feasible normal capacity, we should consider all these elements, and we should consider also that the productivity or the efficiency or the effectiveness of a production process is also related to the combination of all these elements. Now, just to be very, very concrete about the elements, it's very important balancing machinery and equipment. For example, we should consider different processes within the same company and consider the utilization of different devices like machineries and equipment. So, in this example, we have milling, drilling, turning. Then we have base, variable, case. And then we have machine time expressed in terms of minutes. So, we have 3 minutes for base and milling. We have 5 minutes for valve and milling. And then we have 0 minutes when it comes to case and milling. If we have another productive phase, we have drilling, 5 minutes for base, 3 minutes for valve, 2 minutes for case. When it comes to turning, we have 4 minutes for base, 0 minutes for valve, 0 minutes for case. So, if we take in consideration the total time, which is just the sum of all these minutes that we have included in this table, we have 8, 10, 4. Now, the aim is to exploit the installed capacity. The aim is to obtain what we will call the feasible normal capacity of a plant. So we have to minimize the investment costs and to minimize the operational costs as well. So if we consider all these total times reported here, we start from the minimal one, which is 4, and we consider it as a base for the choice of how many machines we need for these specific phases. Now, we have the smallest amount of time, 4 minutes. So the ratio, this is going to be considered as kind of the internal benchmark for process design. So we consider the ratio 1, since we have 4 divided by 4. So 1 is the parameter here. And we choose 4 as the account parameter for the others. So the ratio here is 2 because it's 8 divided by 4, which is 2. And here it's 2.5 because again it's 10 divided by the minimal time, which is 4, and it's equal to 2.5. So if we consider the integral ratio of dividing 8 by 2, it's 4. If we divide 4, this is the ratio, so 10 divided 2.5 is 5, and so on. So this is the amount of machines that we need in order to synchronize all these plants, all these machines within the same plant. So it's the number of machines required. If we consider the categories of machinery and equipment, we have different possible forms. It's pretty much the same classification that we have considered for the materials, and when it comes to machinery and equipments, we have the similar classification of raw materials and products, for example. So we have production, auxiliary equipment, storage and warehouse, service equipment. So if we consider the gas turbine ratings that you might find in your materials on the website, we might have different combinations of all these elements in order to have an installed plan and description of production process. What are the ambient effects on machine capacity? Ambient conditions, consider the natural environment, can affect the performance of machinery and equipment. This is an old idea we're familiar with already. Let's try to be a little bit more specific. So these ambient conditions could be relative to temperature, humidity, atmospheric pressure, air purity, and wind velocity. So considering the different elements to which a production activity could be exposed, and considering the fact that the operational requirements by all these equipments and machineries could be affected by the external conditions, all these elements are crucial for the determination of the feasibility, or better, the feasible utilization of the machinery we install in. Another effect is related to part load. So, effect of part load performance and overloading. Machinery and equipment should be applied within appropriate ranges of workload. So, if the workload is too high, we are operating in overworkload conditions, then we might have coordination costs, or the pressure on the machine and equipment could be so high that could boost the risk, the operational risk related to the devices. On the other hand, if the workload is way lower than installed capacity, then the use of machinery could be inefficient, so the whole project could suffer by higher cost of utilization of such an investment. Another element is the deleterious effects on performance can result when the application is outside the range of acceptable loads. So even too high or too low. So how can we assess the proper load and the proper usage of the installed machinery? Well, in order to define the so-called feasible normal capacity, F and C, we could employ some table and some other descriptive data to be collected in order to figure out what the feasible normal capacity would be. So just to give you an example, we could have different set of data. So machinery and equipment data, part 1. We have the machinery equipment, machine 1, machine 2, machine 3, and so forth. Then we have the code, so also the machines should be coded. The description, brief description of what the device is about. The required feasible normal capacity, both in terms of quantity and unit. So Q and U here in this column stands for quantity and units. Feasible normal capacity per unit, again quantity and unit. Number of units required that we have just calculated by referring to the previous table. Then we have the total F and C, again both in terms of quantity and units. When it comes to the dataset number 1, we might have a second part as well. So we start from the total feasible normal capacity that we have just reported on the other part of the table. And then we have the connected load per unit, the kilowatt, the load factor, so the percentage of exploitation of such machinery or equipment, the total connected load, which is again in terms of kilowatt, the power factor, and the total kVA, which is the kilowatt for ampere. So it's 1000 volts ampere. We might refer to a different data set as well in order to expand our collection of information, in order to be more precise and in order to enhance the level of accuracy for the feasible normal capacity. So dataset number 2, machinery and equipment, we start always from the kVA, so it's again the 1000 volts ampere, and then we assess other sources of information and resources. Water per unit in terms of cubical meters per hour, total water again cubical meters per hour, water quality factors. So since water could be a crucial resource for the production process, the level of purity or the level of quality, it's very important. The second data set is about other utilities, DQU, description, quantity, and unit, here, source, and another distinction that could be relevant for the following rows is about the source of procurement. That might be foreign or local. So the cost per unit, both for foreign and local resources, the total cost, foreign, local. Then we might have additional elements like duties and local taxes, transport, insurance, etc. Again, foreign and local. And then from the total cost, we might have the total delivered cost. So if we combine the part related to the production and the part related to the transportation, the delivery, we have the total delivered cost. Other additional elements in this second data set, so again, machinery and equipment, Second, third, we have the installation requirements, again in terms of description, maintenance requirements, installation costs for a local, again, delivery schedule, and expected life of the equipment and machinery. So by collecting these two data sets, we might be able to figure out what the exploitation and the usage of the machine might be. Estimating machinery and equipment costs. So we have different elements here to be considered. The first one is to break up projects into components. So in order to figure out what the cost will be, we should break down the project into sub-projects. A useful tool could be to refer to the work breakdown structure that we're familiar with already, and try to employ it in terms of components and subcomponents of the project itself. Second, link components to physical facilities. So once we have decomposed the project in different components, we could assign them to different facilities within the plant. So it's also about tracing each component as well. Then we might visualize in physical terms through the flow charts, for example. Another important element is to use the rule of thumb to estimate in early stages. So this is going to be a recurrent activities that we should do for estimating the cost of activities in the early stages. So early stages recalls the idea that the plant is not even existing, so we have to estimate cost factors. So as we will see during next class, we should refer to different rules of thumb in order to understand what is the impact of the economies of scale, for example, what is the impact of the under or overutilization of plants, and so on. Refine with tender offers from reputable sources. So once we have kind of a rough idea about the cost, we could refer to external sources like reputable actors or reputable players or competitors or consultants or suppliers in order to refine our idea of cost. And then cross-check estimates where possible. So if we have different components of the same projects, the exploitation of the links and the similarity among all these components could enable us to proceed to cross-check of the estimates that we just made. So, a concept that we are familiar with, a way to proceed that we are familiar with from the past class, is to consider list and field of application. So in estimating machinery and equipment cost, we should list all the items and code them through item number or code. Define the number of machines or equipment. Then additional information about the specific sources and utilization of such equipments and machineries, like market, unit cost, total cost, and project periods required, including replacement. So it's not just about where and when in terms of quality and quantity, it's also about the schedule of such activities within the project. The application of such list is the production equipment, the auxiliary equipment, the service equipment, the initial stocks of spare parts, consumable parts, tools, dies, and fixtures. So the methodology that we have just developed could be employed in different areas. So this is for the estimation of machinery and equipment in terms of study. Another crucial element in dealing with product and production is the setup of the plant capacity. So we have some plant capacity issues that we will start today in this class, and we will continue in the last one dedicated to product and production, which is the next one. So when it comes to plant capacity, we are exposed to both internal and external factors. Let's start with the internal factors. This picture will help us to understand plant capacity, internal factors. We start from demand, market share, and penetration estimates. So this comes from demand forecasting, as we've seen already, and this comes from the marketing strategy that we're familiar with already too. Both the estimation of demand and the consideration of the strategy of our company, we are able to define the sales program. So as we've seen already during the marketing part, we forecast the demand, we define a strategy, and then we end up with a sales program. The sales program, from this perspective, nurtures some important choices about capital investment cost, setup cost, inventory and storage cost, as well as production cost. So according to the standards embedded in the products that we plan in the market, in the sales, marketing and sales program, we have all the requirements which are necessary for estimating the costs related to capital, setup, inventory and storage, and production cost. Once we have a clear idea of what the cost will be, we might proceed with a program. So the production program is the output of such estimates here. Production program is about how much we need to produce, when, and according to what conditions. So plant capacity is crucial in order to implement the production process and the production program. So what is this feedback represented by this yellow arrow? It's a feedback connecting the exploitation of plant capacity, as we will see, with the cost related to the invested capital, setup, inventory and storage, and the production cost. So, as we will see in the next class, for example, the actual condition of exploitation of the maximum potential of economies of scale could reduce the unitary production cost. On the other hand, if our installed capacity is underexploited, then the unitary production cost could be higher than expected. So this feedback, this yellow arrow here, depicts the situation that the exploitation, the ultimate and natural exploitation of the plant capacity is crucial in order to have a refinement of the estimation about the cost. It's not just about production cost, it's about inventory and storage cost, for example, since if our capacity, again, is not exploited in a proper way, we might have consequences on the product fixed cost utilization, the sunk cost utilization, while we have an impact on the variable costs like the ones related to inventory and storage as well, and so on. So this is for the internal factors. When we refer to the external factors influencing the plant capacity, we might refer to this picture here. Again, the inputs come from the marketing program. So we might have market study, production and sales program, and then we have the choice of technologies. Now, what is external in this in this analysis. The fact that the applicability, the ranges, the minimum and the maximum capacity in terms of plant for local conditions could differ. So the external environment could influence the range of technological alternatives that we have, or considering the same technology, the environment, both the natural and the economic environments could constrain our possibility to exploit the installed technology. So from these programs, we might choose the technology, and the combination of these programs and the external impact of technologies could define the so-called feasible normal capacity, FNC, that we've seen already. Now, the question is the proposed capacity within the range, minimal and maximum of FNC range? So is it sustainable from a capacity point of view? If the answer is no, then we should reconsider the plant size, which means that it's either too big or too small. So we might be inefficient considering the idea of plant size that we have. So the process starts from this phase here. So we should reconsider the production and the sales program, reconsider technology, and so on. If the proposed capacity is actually within the range of the feasible normal capacity, so the answer is yes, then we should ask ourselves a second question, which is about the exploitation of economies of scale. So, do we have economy of scale constraint? If the answer is yes, so we are constrained by the economies of scale, then we should again, yes, reconsider the plant size and then start the process from all over again. If the answer is no, then we should accept the feasible normal capacity for further study. So, the external factors could impact on the definition of the feasible normal capacity. So, to this extent, it's quite clear that the feasible normal capacity is defined by human factors, operational, environmental, and systematic engineers factors. So, the feasible normal capacity we refer to is conditioned by both internal and external factors. Another element that we should consider is the so-called nominal maximum capacity, NMC, which is defined by system engineering. So it's just the installation and the nominal exploitation of the capacity. So in general terms, and it could be other than this way, the feasible normal capacity is lower than the nominal maximum capacity, which means that, for example, if this one is 100, the FNC may be 80. So the NMC, the nominal maximum capacity, it's related to the equipment installed capacity. So it's nominal. It includes reserve and standby capacity. So a lack of capacity that cannot be exploited by the company, and may be different for various types of production equipment in the plant. So we might have the same plant, but different machineries and different equipment might be exposed to different installed capacity issues. So the nominal maximum capacity is just related to the potential exploitation of machineries and equipment. When it comes to the FNC, the feasible normal capacity, we have different factors affecting the FNCs again. To be a little bit more specific, we might have environmental conditions coming both from the natural environment and or the economic environment. Temperatures, humidity, things like that. Strikes are another important element for the exploitation of the capacity and are related to the economic conditions in the external environment. Second, management and work skills. So, since we have a constant interaction between human factor and the technological factor, a skill gap or a skill shortage in terms of specialized skills for these kinds of machineries could be another element constraining the exploitation of the nominal capacity and explaining why the feasible normal capacity is lower than the nominal maximum one. Again, we might have planned and unplanned maintenance. So each event of maintenance is stopping the machinery. So it's interrupting the functioning of our production process or important parts of our production process. Then we have the so-called reserve capacity. Now, if markets would be steady and present constant values, then the installed capacity could be able to deliver, to manufacture and deliver products at the best economic conditions. But as we've seen already, and we will see later in the next class, since markets are exposed to fluctuations, then sometimes a reserve capacity is planned in the investment as well, which means that by definition, the nominal maximum capacity is lower than the feasible normal one, since we have slacks of capacity to be used for example, in case of demand peaks that the company should face. Other constraints on inputs and resources. So, if we consider the materials flow and the other resources like financial resources or human resources that we are using together with machineries and equipments, all the shocks and all the troubles that the company might experience in such fields could have an impact on the exploitation of the installed capacity. So, today we've seen mainly two aspects. The first one was related to the study of the plant installation and the synchronization of the different machinery and equipment. So it's not just the choice, but the management of such elements. The second one, which is going to be continued in next class, is about the plant capacity and the decisions related to it. What is important to recall is the difference between the nominal maximum capacity and the feasible normal capacity, which is lower by definition. You can refer to our website for further information. That's everything for today. Thank you.